Hey, hello everyone. Welcome to the fourth last session of our quantum computing workshop, QNickel. Uh, yeah, as I said, this is the last session, and the last homework, the last quiz will be also available from the evening, and then you will have 1 week to just complete all the quizzes. Okay, Justina, if you are ready, I think we can start.
Hello, everyone. Let me share my screen. Please confirm that you can see it.
I can see it.
Cool, thanks. So let's quickly go through today's agenda. So we are still are going to use the circ framework, and we will be solving the MaxCut problem using Groover's search. And we are going to program the 3 notebooks. So the first one is MaxCut problem and bipartite graphs, and the second one is others and numbers checking, and the last one is Groover's algorithm for the MaxCut problem. Yeah, I think we can start with the notebook B02. We will go through for the notebooks B02, B03, and B04. So let's start with B02 MaxCut problem. So let us consider the following graph. We see that this graph consists of 4 vertices, 0, 1, 2, and 3, and has 5 edges in total, 4 here and 1, the diagonal one. And the task is to color each vertex with either blue or red and count the number of edges that connect vertices with different colors. So let's see this example. So in here, we see that we have 3 red vertices and 1 blue vertex. So the only edges that connect vertices with different colors are those ones. So the number of the edges that we are looking for is equal to 2. So there are 2 edges that connect the vertices with different colors. And in the second case, we can see that we have 1, 2, 3, 4 such edges because the coloring here is different between these vertices. And the formal definition of the MaxCut problem is like we need to find the maximum number of edges so that the endpoints are colored using different colors. And alternatively, we can see this problem as the problem of partitioning the vertices of the graph. Maybe I will show the graphs here into 2 disjoint sets. So one vertex cannot be in both of these sets. So we need to choose assign a vertex to only one set. And we want to maximize the number of edges that are between those sets. This is a hard problem. In fact, it's NP hard, and with in this notebook we will be focusing on a little bit modification of this problem. So for a given graph G, we will need to determine whether there exists a cut of size at least k. So it will be just a decision problem with a yes or no answer. So it is still a challenging problem. It's NP complete because in fact, if we were to check it by one, there are 2 to any possible colorings. So that's exponential time that is needed. And basically, the 3 notebooks we are going to use use and implement today they are just an extension of the previous one. So in this notebook, we will define the max cut problem. In the second notebook, we will actually learn how to calculate the number of edges, and in the last one, we will use the reverse search to search for the biggest cut or the cut width has the size at least k. So now let's focus on a simple case of bipartite graphs. So let's recall the definition of a bipartite graph. So a graph is bipartite if the set of vertices can be divided into two disjoint sets, such that each edge connects a vertex from the first set with a vertex from the second set. So in the example here, we can see that this can be achieved. For example, if we decide to color 1 and 0 red and 2 and 3 blue, then we see that those are like disjoint sets. And the cut is 1, 2, 3. Alternatively, we could do the same and use the opposite colors. So those can be blue and those can be red. So the solutions are the same, but we are just using different colorings. So every time there should be like two answers that mean the same thing. And let's take a look at this graph. So maybe I will paste it somewhere here. So let's just create some space. And we can see that it would be very hard for us to like find a coloring that will satisfy the fact that there should be, so this is very bad, like within the if we have a bipartite graph, the vertices in one set should not connect with each other. So this is not bipartite if we divide it this way. So maybe let's try a different way. Maybe we should do it like that. And it will also turn out that it doesn't work. And in general, we won't find a coloring that satisfies that because there are like these edges. So everything is going to be connected. So this second graph is not bipartite. And now we will try to check whether, oh, sorry, there are some questions on chat. No questions. We will try to check whether a graph is bipartite by finding a two coloring. That's the property of the bipartite graphs. If a graph is bipartite, there is a two coloring. So we can divide this graph into disjoint sets. And we will use the idea to represent coloring of a graph in a quantum circuit. So we are going to use two colors, so it's easy to represent them with binary numbers. So for a graph with n vertices, we will use n qubits. And if the ith qubit is in a state so if the ith qubit is in state 0, it should be red, and if it's blue, it should be 1. So your task now would be to implement the idea given above. So we have a graph with 4 vertices, so there will be 4 qubits needed. And you need to represent the following coloring of the graph of the circuit. So you need to set the values of the qubits to proper values, either 1 or 0. And now I think 3 minutes should be good for that task. So please start working on that and log your activity on Discord. Let's do this task together now. So we need to mark state. If the color is red, we need to mark the state as 0, and if the color is blue, we need to mark the state as 1. So let me paste some code. So we are going to append some quantum gates, and at the beginning, all of the qubits are in state 0. So in fact, we don't need to do anything with qubits 0 and 3. So I could omit doing that, but let's keep it here. And if we want to change the color for blue from 0 to 1 for vertices 1 and 2, we need to use the poly X gate. So let's see the output. And this says that 0 is red, 1 blue, 2 blue, and 3 red, and it seems to be correct. Do you have any questions about that? Okay, so let's go further. Edge checking. Now we will implement a protocol which checks whether an edge has endpoints with different colors. For each edge, we will use a separate qubit on which we will store a Boolean value 1 if edge connects vertices with different colors, and Z otherwise. So to do that, we can use the XOR function. We know how XOR works. And in this case, X and Y are the colors of the vertices, and the result is the Boolean value. Like the colors are 0 and 1, so the Boolean value for XOR will work out great. And we can implement this XOR function using two CNOT gates. We've done that, I think, on our first day of the workshop. We implemented CNOT using, we implemented the XOR using two CNOTs. So let's see what is done here. We create 3 qubits in total. The first one is to represent the first edge. The second one is to represent the second edge. And the third is to store the result. So in the first step, we are checking whether what's the color of the first qubit. If the color is, we will analyze that in a second. In the second step, we are checking what's the color of the second qubit. So we can verify that it works correctly. So if we have 0 and 0 here, so at the beginning everything is 0, and the last qubit is also 0. So 0 and 0, none of the CNOTs fire, so the outcome is 0. If it's 0 and 1, which means that the colors are different, it's red and blue. This won't fire, but this will fire, so the output will be 1. If the first is blue, the second is red, it's 1, 0. This CNOT will fire, this won't, and the output still will be 1. And if both of them are blue, it's 1 and 1, then both of the CNOTs will fire, and at the end we will have 0 here. So we in fact verified that it works like an XOR, because only if the two colors are different, the outcome is 1. And in here we have an analysis for all the possible inputs. So all possible inputs are 0, 0, 0, 1, 1, 0, and 1, 1 in the case of 2 vertices. And let's just take a look at the output. So if the first vertex is set to 0, second to 0, we don't have any X gates, because that's what you've done in the first task. You put some X gates if there is a change of color. And if both are set to 0, the output is 0. If it's 0, 1, the output is 1, 1, 0, output 1, and 1, 1, output 0. So now our task would be to design an oracle for checking this bipartiteness. So in Grover algorithm, our aim is to find an element marked by the oracle. If we have an oracle detecting any edge connecting two differently colored vertices, then we can use Grover's search to find such colorings if exists, which marks colorings in which the endpoints of all the edges are colored using different colors. Then we can use Grover's search to find such colorings if they exist. Therefore, we need to define an oracle which will check and mark the colorings which satisfy this property. So basically, we want to have a non-transparent box that will just mark for us the colorings that are okay. And by mark, I mean changing their, flipping the sign of their amplitude. And as it was described above, we will use separate qubits. So we've used separate qubits for each vertex and for each edge. And the states of the qubits corresponding to vertices represent the colorings. The input to the oracle are the qubits representing the vertices, and the rest of the qubits are used by oracle. before the oracle starts its computation, all qubits representing the edges and the output qubits are in 0 state, and they should also be in 0 state at the end to be used again. That's a very important remark. I will say a bit more about it later. We can summarize the computation that is performed by Oracle in 4 steps. So first of all, you need to use the XOR operation to assign appropriate Boolean value for each edge. Then you need to use additional output qubit, which is set to 1 if each edge has the value of 1. So each edge connects to vertices with different colors, and this part can be implemented by multi-controlled node operator. So you just need to flip the value of the target qubit only if all controlled qubits are in states 1. And now it's time for task number 2. So let me explain what is necessary to do in here. So you are given such a graph, and you need to implement the first 2 steps, this 1 and 2, described above. And the first 4 qubits are used for vertices. So in total, we create 8 qubits. First 4, so qubits 0, 1, 2, 3, are used to describe the possible colorings. So if QQ0 or QQ1 or QQ2 or 3 are set to 1, it means that the color of this particular vertex is blue, and if it's set to 0, it's red. And actually, you don't need to set the colors in these lines, so lines 7 to 9 and lines 11 and 12, you have some proposed input to the algorithm. So you are going to check whether a coloring is correct or no, and the correct one is, for example, when the only correct coloring is when 0 and 1 are the same color, and 2 and 3 are the same color, but a different color from these previous ones. So what you need to implement now is to use the XOR operation to assign appropriate Boolean value for each edge. So you know that we will use three qubits to represent the value of edges. So the next 3 qubits are qubit 4, 5, and 6. And by using the XOR operator defined exactly in here, you need to check and store in this appropriate qubit whether the edge connecting 0 and 2 is 0, which means that vertex 0 and 2 have the same colors, or if they have different colors, it should be 1. So to implement that, you need to use only CNOTs, and apart for all these 7 qubits, you need another one, the 8th one, an ancilla qubit. And this qubit is used to store the output, and the state of this qubit should be 1 only if the edges connecting 0, 2, 0, 3, and 1, 3 are in state, so the qubits representing the edge connections are in state 1, which will mean that 0 and 2 are in different colors, 0, 3 have different colors, and 1 and 3 have different colors. So the first part of the code written in here is just the encoding of colors, but you need to write the steps number 1 and 2 described here, and you will have 8 minutes for that. Do you have any questions? Okay, let's do this task together. So what we need to do is to implement this first step, check what are the colors of the edges, and we know how to do that because we've seen it implemented in this edge checking part. So basically we need to use the controlled X operator and store the results on another qubit. So let's check whether, so we have 3 edges, 0, 2, 0, 3, 1, 3. So let's check what's the color of edge 0, 2 and store it at qubit 4. So to do that, we are using controlled X, where the control is the vertex and the first vertex, and the target is this ancilla qubit for the edge 0, 2, and this is the second vertex, and this is just for storing the output. We need to do the same for edges 0, 3. So the value of edge 0, 3 is stored at qubit 5. So it's CX, control qubit is qubit 0, target qubit is qubit 5, and the second part of this edge is the vertex 3. So it should also be stored at qubit 5, and we need to check the last edge, which is edge 1, 3. So we apply the controlled X on the target control is a qubit 1, and the target is qubit 6 because that's the qubit for edge 1, 3, and another one is this other vertex 3, and it's also stored on vertex 6. And then we need to do this second part. We need to check whether all of these edges are set to 1. So the easiest way to do that is to use a multi-controlled NOT operation. So we are using this qubit numbered by 7 to store this result. So this qubit number 7 should be controlled by qubits 4, 5, and 6, which actually tell us what are the colors of the edges. So let's print the circuit and maybe let's analyze it step by step, maybe without. So for the input in which the vertices 0 and 1 are colored the same, so it makes sense that 0 and 1 should have the same color. The output is that the graph is bipartite, but if we use this other version of the input, where the first qubit has a different color only, so only this qubit has a different color, then for sure this graph is not bipartite because in this version of coloring, it's wrong coloring because then we have an edge connecting 1 and 3, and they are in the same set. So for now, let's omit the coloring, but just let's focus on how this circuit looks like. So we have qubits 0 and 3, which store vertices. So it's just an analysis of these circuits. So it's vertex 0, 2, and 3. And now we have edge. The first edge was 0, 2, edge 0, 3, edge 1, 3, and the result. And let's see why it works. So for example, let's start with this. So the value of qubit 4 should be 1 if the vertex 0 and 2 have different colors. So the vertex 0 is in here, vertex 2 is here. So this qubit number 4, it stores 0 if they are of the same color and 1 if they are of opposite colors. And I think it makes sense because it's just 2 CNOTs applied to qubit number 4. The same works for edge 03. We have so edge 03, it's actually checking what's the value of the qubit of the vertex qubit 0 and qubit 3. We can see that's the only operations performed on this qubit number 5. So if qubits 0 and 3 are of different colors, then qubit 5, which is the value of edge 03, should have the value 1, otherwise it should be 0. And the same works for the edge 13. So we are checking the vertex number 1, vertex number 3. What are their colors? If they are opposite, then this value should be 1. And if they are the same, the value should be 0. And now we need to take a look at this last layer. So in here, the important thing is that the last qubit stores the result. So that's the result qubit. And the result qubit in here focuses on whether the values of the edges are 1, which means that they have the opposite colors, or no. And we are looking for an assignment of edges where the edges between the vertices have the opposite colors. So if it's true, so all of the edges have the opposite colors, then the value between this multi-controlled node, the values before this multi-controlled node should be 1, and the result should be 1 because it starts with 0, so we flip 0 to 1. And if some of the edge is, if it's not true that the edge, for example, for 0, 3 is 1, which means that 0 and 3 have the same color, then this graph should not be bipartite. So yeah. Do you have any questions regarding task number 2? Okay, so let's go. So for now, we've seen these steps 1 and 2, which is edge checking, and the second step is checking if all the edges have the value of 1, and there are steps 3 and 4. And in step 3, the oracle, so we are coming back to this Gruber's algorithm, flips the sign of the amplitude of the states which lead to 1 as the output. And this can easily be done by applying the Z gate, because when the state is 1, the sign is flipped. And when the state is 0, the sign is not flipped. It's how the Z gate works. So Z applied to cat 0 is cat 0, Z applied to cat 1 is minus cat 1. So that was the step number 3. And the final step number 4 is we reverse the whole computation done in first 2 steps, so that the oracle leaves all the qubits used in the computation in state 0. And this can be done by reversing every qubit, every quantum operator before the Z gate. And in CIRC, it's done with the inverse method. In this way, the only effect of the oracle is flipping the amplitude of the sign of the qubits representing the correct coloring. So now we will analyze the code that implements that and see like why and how it works. So first of all, we have the oracle implemented, and in fact, it's the same code that we've written in here, but it's just here in the form of a function with this yield generators. And what we do in the oracle computation. So at first, we are returning the oracle that is in here. Then in the qubit that represents the solution. So this ancilla qubit, if the ancilla qubit is set to 1, this should be like inversed, like not inversed, flipped to -1. If it's 0, then it won't flip because the Z gate won't do anything. And then we inverse the effect of the oracle. So I will say in a second, and you will see why it works. So let's take a look now at the result and check what happened. So the first 4 qubits are used to represent the colorings in general. So there are 16 possibilities, and we know that only 2 of them are correct. The one with the first, the qubit, the vertex 0 and 1 having the same color, and vertices 2 and 3 having the same color. So it's option that it's encoded either are as red, red, blue, blue, or blue, blue, red, red. There are only 2 correct solutions, as I've said, and they have their amplitude signs flipped. So let's assume, so that's the effect of the whole oracle computation. So let's see what would happen if we perform the operation like that. So when we apply the oracle, one more thing, please note that the rest of the qubits in this like whole, after this whole oracle computation in this version has the values 0. So the last 4 qubits are the qubits representing the edge coloring and the ancilla qubit for the total result. So let's omit that for now. So let's assume that the oracle computation is just applying this oracle for edge checking. So after that, we can see that if we just use the oracle, first of all, all of the amplitudes are the same. There is like no sign flip, neither here nor here, and it should be. So so let's flip the sign in the proper place. Yeah, we see that. So we did that by applying the Z gate. But now the rest of the qubits of the qubits that help us do the calculation have like different values, and we would like them to be restored to zeros. So to do that, we just need to apply this oracle in inverse, and it does the magic. We have all the zeros here, but the amplitudes for these states that should be marked are flipped. They have the minus sign while the others don't. And now your task is to try to implement the task number 3. For the given graph below, so we see the graph, you need to iterate the reverse search algorithm 2 times. So that's already implemented for you. So you need to basically implement Oracle in computation and Oracle functions. And they say that you need to use 9 qubits in total, 4 for vertices, 4 for edges, and 1 for the output qubit. The diffusion operator is already provided. So what you need to do is to implement for this graph for task number 3, the Oracle and Oracle computation functions. And let's have 8 minutes for that. the time is up. So before I come to the implementation of task number 3, I will answer the questions that were on the chat. So the first question was to repeat or rephrase the importance of reversing. And yes, so what you saw yesterday in the Groover's algorithm was that there were like layers. So you initialize with the Adamart gate at the beginning, layer of Adamart gates at the beginning. Then you apply Oracle, and then this diffusion operator. Then another time this same Oracle and diffusion. So it was like a layered algorithm. So it will be very nice if like when we just do many iterations, we could reuse the data. So in here, if I'm not mistaken, you need to, yes. So in this code that you are going to implement in task number 3, you needed to do two iterations of this Groover search. Like not 2 iterations, but like do these 2 layers of Oracle and diffusion. And so let me maybe show it. Groover algorithm. So in this version, you needed to exactly do a circuit like that. In initialization, Oracle, diffusion, Oracle, diffusion. So it is very nice that if after the first layer of Oracle and diffusion, the data could be reused by the second Oracle and then diffusion. So if we in the Oracle, because it's yeah, if in the Oracle we just use the Oracle, so it's just the Oracle, and if we just use the Oracle, we still have the same probabilities. Then we mark our state with mark the states that are correct solutions with the flipped amplitude. So it's not diffusion because we are not like increasing any amplitudes. It's just the Oracle. But what we see now is that the qubits that we were using to store the additional data, qubits 4, 5, and 6, they are after the Oracle and the change of like flipping the sign of the amplitude, they can't be used any longer because they serve their purpose and they have some values in them, and they are not the same values everywhere. But we would like to be able to just reuse those qubits in the next Oracle computation. So we just want to have these two states marked, and by these 2 states I mean the first 4 qubits, because that is the reference to the coloring, and the ancilla qubits can be restored to their original value, which is all zeros, but we still want to have the amplitudes unchanged. So if we apply the Oracle, but the inverse version of the Oracle, we are not changing the amplitudes, so only 2 of them have the negative sign, but we have zeros in the qubits representing edges and the final result, and then it can be reused in some next operation. Does this answer your question? I hope so. If not, please write follow-up questions on chat and I will be happy to answer them later. And another question was, what we are doing now is we are partitioning the graph structure into two distinct groups. Is there a way to encode a possibility for partitioning into 3 colors or more inside the quantum algorithm like that? And this problem can be called max 2 cut. And the generalized version is max k cut, which is an assignment of the vertices into k disjoint sets. So if you have like more colors, you can store the values of these colors just using more qubits. In here we have the simpler version where only 1 qubit is sufficient to store the color. But yeah, you can do that. So if there aren't any more questions, I will try to write the code for task number 3. So I will start with implementing the oracle. So let me paste some code here and I will explain it. So in the oracle, first of all, we are checking the if in qubit 4, when in qubits 4, 5, 6, and 7. Sorry, there's something on chat. Okay, cool. Yeah, so coming back. In qubits 4, 5, 6, and 7, we are going to store whether the edges 0 and 2, 0, 3, 1, 2, 1, 3 have the vertices have the same or different colors. If they have the same color, this should be 0. If they have different colors, this should be 1. So we are using controlled X as we've used earlier. So in qubit 4, store the edge 0, 2. In qubit 5, store the edge 0, 3. In qubit 6, store the edge 1, 2. In qubit 7, store the edge 1, 3. And the last qubit is set to 1 only when all these qubits are set to 1. So in fact, this last qubit is controlled by all these edges, the values of the edges that are stored on qubits 4, 5, 6, and 7. So that's the whole computation of the just implementation of the oracle, and we need to compute the oracle. So basically, we just need to, first of all, apply this oracle, then change the sign on the ancilla qubit for the correct coloring, and then inverse the oracle, which will just restore the values of qubits from 4 to 8 to 0 from whatever their previous values were. And what we can see here is that the coloring 0011 and 1100, both of them have very similar occurrences. We measured the circuit 1,000 times. So both of them, when they are summed, they're very close to 1,000. So it means that this graph could be divided into like 2 sets. Yeah, the qubits 0 and 1 should have the same color, and qubits 2 and 3 should have the same color, different from the qubits 0 and 1. We have also some other results with very low occurrences. What it means is not that there is like something wrong with our algorithm. It's just the amplitudes for the correct solutions are very high, but they are not like 1 over square root of 2 and 1 over square root of 2 for these two. No, they're just slightly smaller. It means that the other states have very low amplitude, but sometimes they can occur. But these occurrences are much lower than the occurrences for the correct results. Do you have any questions regarding task number 3? Okay, so now we can go to the final task of this notebook. So you need to repeat task 3 for this graph. And the question is very, very important question. Does the following graph has any correct colorings or not? If not, what would you say in advance about the frequencies of the outcomes? So before you run your code, please try to answer this question. And you can have 5 minutes for that. we can implement this task together now. So let me start. So it's extremely similar to the task number 3, but the only difference is with the connections between the vertices. Here we have the connection like that, and in here it was a little bit different. So what we can do is first to actually implement an oracle for that. So in qubit 4, we are storing the value of H01. So we are using controlled access for that. In qubit 5, we are storing the value for H02. In qubit 6, the value for H03. And in qubit 7, the value for H13. So that's storing the edges. And then we need to get the result, and the result is obtained by just checking if all of these edges, so qubits 4, 5, 6, and 7, have the value 1. If so, please change the value of qubit 8 to 1. So it's a multi-controlled X on the last qubit. And the part for the oracle computation is the same as it was in task number 4. We still have the same number of qubits because the number of edges was the same, but the connections are different. So we just need to apply the oracle, then apply the Z gate that will inverse, like flip the sign of the states that should be marked. And then we are inversing the oracle, which means that we have this state we're looking for marked, but we want to restore the state of the helper qubits to all zeros. And oh yeah, the question here was so the first thing you can notice is that this is not a bipartite graph, so there is like no coloring that would answer this question, how to use two colors to divide this graph. So what can we say about the frequencies of the outcomes? Is what we see is that all of the results that are measured have very like similar frequencies. There is no one dominant solution. There are many solutions, but they are not correct, and all of them have more or less similar probability. And in this case, as you have noticed, there were so in the task number 3 there were correct solutions, and they had very high probability. Do you have any questions regarding this notebook or task number 4? I can't see any. So we finished this notebook. I think it's time for a short break. Let's take more or less 7 to 8 minutes break, and let's meet at 4:25. the break has just finished. So now there are no more exercises in notebook BO2, so we can switch to the notebook BO3, which is others and numbers checking. To implement the oracle for solving maxcut problem, we first need to examine how to add numbers in a quantum way. So first of all, let's focus on half others. Suppose that we want to add two bits, A and B. Sigma represents the sum and C out represents the carry. That is an overflow to the next digit. And let's represent this relationship between the bits in this following table. So A and B are the bits we want to add, C is carry, and sum is the sum without the carry. So 0 plus 0, sum is 0, carry is 0. 0 plus 1, sum is 1, carry is 0. 1 plus 1, sum is 1, carry is 0. 1 plus 1, sum is 0, carry is 1. It's, yeah, I think this is visible, that the carry is 1 only if both of the inputs are 1, which and if you just take a look at these two last columns and like consider them as being binary numbers. So when you add two zeros, the output is 0, 0, which is 0. When you add 0 and 1, the output is 1. 1 and 0, output is 1, but 1 and 1, the output is 1, 0, because it's actually 2. So you see this table, how it looks like. And the third column, which you can see here as the carry, is in fact the AND operator. So for 0, 0, 0, 1, 1, 0, it has the values 0. And for the values 1 and 1, it has the value 1. So it behaves exactly like the AND logical operator, while the last column represents the XOR of the first two, so of the input. So this has the value of 1 only when the inputs are different, and when they are the same, the output is 0. So your task now is to implement the above half other and verify that it indeed generates correct outputs for any input. So in this space, you just need to implement the following quantum gates, and you have 3 qubits instead of 4. So you're adding only 2. Yeah. So no, it's basically you just need to implement this circuit that is in here, because you're adding two digits, and you need 1 qubit for the carry and the other one for the actual sum. So let's it's B003. Let's have 3 minutes for that. let's do this task together. So we need to have a controlled X when the first two qubits are the control and the third one is the target, so it can be implemented as CCX gate. So it's clearly the same thing. And then we need to add two CNOTs. The first one has qubit 0 as the control and qubit 3 as target. The second one has qubit 1 as the control qubit and qubit 3 the same qubit as the target. So maybe let's also print this circuit one time. So we see that we have this Toffoli gate and two CNOTs, and it's the same. And what do we get here? It's so what's the measurement output? Because we are okay, we are not changing. We are not changing. Please note that we are not changing the value on the first two qubits. So in fact, we could just measure the second and third qubit, but we measure everything to just know what the input was. So if the input is 0, 0, the carry is 0 and sum is 0. If the input is 0, 1, carry is 0, output is 1. If the input is 1, 0, carry is 0, sum is 1. If the input is 1, 1, carry is 1, and the sum is 0. So it should look like it works, and it does. So the half other above stores the solution on a separate qubit. And we can think of this operation as A plus B. So yeah, we really need this this last qubit in here to store the result. But it's also possible to implement in-place addition. So instead of using this ancilla qubit, we can store the result of adding A plus B in B. So this can be done using the following circuit that consists of this controlled NOT and controlled NOT. And let's see the truth table for this quantum circuit. So we can verify that if cat Q0 and cat Q1 are the digits being added, then on Q1 we will have the sum bit, so in here, and on Q2 we will have carry. So in the previous example, carry was here and sum here, but now we have sum here and carry here. The order does not matter in here. So let's verify that. So for input 0, 0, and in this so we have two versions of the same table. In the first table, this column, the third column, is all zeros. So this carry qubit is all zeros. In the second version, it will be all ones, and we will see what's the difference when the carry is implemented as 1 or as zeros. So let's start with the version where everything starts with zeros and the last qubit is always 0. So for 0, 0, we get so the sum 0 plus 0 is 0 and carry is 0. 0 plus 1 is 1 and the carry is 0. 1 plus 0 is 1 and the carry is 0. 1 plus 1 is 0 and the carry is 1. So what we can see is that the first qubit remains unchanged, the second qubit has the value of the sum, and the third qubit only changes its value when we have two ones, because then we have the carry because 2 cannot fit into the integer value 2 cannot fit into a single bit. So what happens if the qubit Q2 is originally in state 1? The sum 0, 0 is 0 and carry does not change, but the carry is not 1. 0 plus 1 is 1, carry is 1 because it started in 1. 1, 0, sum is 1, and the carry is 1 because we don't change it, and sum 1 plus 1 is 0, and the carry actually changes because both this Toffoli gate will fire and this CNOT. So yeah, we will have we'll change, like flip this last value. But yeah, it's not helpful for us to have this carry qubit in state 1, so we will usually set it to state 0 because that's more convenient for us. Do you have any questions regarding the addition of 2 bits? Okay, so let's continue. So now we will be actually counting. Suppose that we are given n bits and we are asked how many of the bits are set to 1. At this point, we know how to add 2 bits, and now we will implement the procedure for counting by adding multiple bits consecutively on top of each other. So basically, if you want, we won't be adding like 1 plus 5, but we will be adding 1 plus 1 plus 1 plus 1, or like basically it will be a string of ones and zeros. And what we will do, we will store the output of qubits Q2 and Q3, where Q2 represents the sum and Q3 represents the carry. We will perform in-place addition, meaning that we will first add the bit represented by Q0 to the output, and then do the same for the bits stored in Q1. So the output is stored, okay, I can't write it nicely. So at first, the output is stored in Q2. And Q3 is the carry. So let's just focus on Q2, which is the sum, and we'll focus on the carry a second later. So first of all, Q2, it becomes Q2 plus Q0. So in the first step, that will be the sum, and the next step is adding the Q1. So in total, like after these 2 steps, so that's the first step, that's the second step. So after the first and second step, this Q2 has consists of Q0 plus Q. And we are assuming that at the beginning, so Q2 at first, it was equal to 0, because like it was initialized to 0. It makes sense with addition to initialize the state with 0, then add the first, and then add the second. So that so this is the thing we mean by in-place addition. We are just adding more values to the output. And of course, in the case when Q0 and Q1 had both the values 1, the state Q2 should be 0, and Q3, which represents the carry, then it should have the value 1. But for now, we don't need to care about that. So let's just see how this sum works. So first of all, this sum, which is cat Q2, is sum, initially it's 0, plus cat Q1. So the circuit that does this operation looks as follows. So we have a controlled X applied to, those are the control and the target. So we just want to know whether there is some carry, and we were talking about this carry just in here. So that's why we have a controlled X. And then we store the carry in qubit 3, and the actual sum is in the qubit number 2. So it's just a controlled NOT operation. So now in Q2 we are storing Q2 plus Q0 result, and in Q3 we are storing the carry from this addition. Then we need to add to this to this sum and this carry another qubit, which is qubit Q1. So the code is very similar. So in here we just had these two first lines, but now we have the whole circuit. So this is Q2 plus Q0, and this is the new Q2, so after this operation, plus Q1. So it's implemented the same way. First we calculate the carry, and which is done by this line. So if both of these qubits are in state 1, then there will be carry, and then we are appending to the sum the actual value that this result sum, which is sum plus Q1, has. So let's take a look at all the possibilities in here. So that's the implementation of what we had in the previous lines, but it's we have a for loop that will allow us to observe what happens for each state. So let's start with input 0, 0. The sum should be equal to 0, and according to this circuit that you... Okay, sorry, it will be small for now, but I will increase it later. So for input 0, 0, we see that everything at first is 0, but the input is 0, 0, so we don't change anything. None of these CNOTs will fire, so the output is 0. Then if we have input 0, 1, actually the first one won't fire, but this group will fire, and we will have the sum 1 and carry 0, so the output is 1. Then for the input 1, 0, those one will fire, but those one won't. So we will have 1 in here and 0 in here, and the actual output is 1. And for the input 1, 1, those will fire, those will fire. The output will be 1, 1. And maybe that's the point where I should write this. So let me go to the whiteboard. And the convention throughout all this part of notebook. So this is like the first number we are adding. So this is Q0, Q1. And it remains unchanged. So this is just our input, but we are getting some results. And the results are B0 and B1. So let's assume that we have this case with 1, 1. So it's 1, 1, 0, 0. And how will it change? So if it's yeah, so in fact, when you take a look, this first CNOT, I'm sorry. I just want to show it in a presentation mode. Okay, this first CNOT, it's not CNOT, it's a Toffoli gate. It won't fire like at all. because we will always have 0 here. So if we didn't have this gate in here, everything would be always the same. So we can forget about that. But let's check for the other gates. So we have 1 on the top qubit, so we'll flip the sign here. We have 1 on this qubit, actually 1 on this qubit, because after the, okay, so I should write this one here. So we have 1s on both of the control qubits, so the target qubit should be flipped, so it will be 1, and we have 1 in here, so we should flip this the state of the qubit number 2, so it should be 0. So B0 is 0 and B1 is 1. And how to interpret the result? So the convention in this notebook is that you will assign, so this qubit number 2 should be multiplied by the 2 to the power of 0, and qubit number 3 by 2 to the power of 1. If we had more qubits, it will be the next powers of 2. And I think it makes sense. So for now, the result is 2 to the power of 1 times B1 plus 2 to the power of 0 times B0. This part is 2 times 1. This is 1 times 1 times 0. So the total output is 2, and we are adding 1 plus 1, so we are not surprised but it's 2. And of course, we are expecting the binary representation of 2, which is 1, 0. So in here we need to read it like from bottom to top, and it actually makes sense to read it that way, because when we talk about adding binary numbers, so at first we are starting with adding 0, and to 0 we are adding 1. So as I've mentioned, it's not like we have the addition 1 plus 5. We will always have either 0 plus 0 or 0 plus 1 or 1 plus 0 or 1 plus 1. So let's increase this 0 by 1. So we are starting the addition from the right-hand side. So we have 1 and there is like no carry. And then we are also starting from the right-hand side. So 1 plus 1 is 0, and there is carry. So we need to have this store the carry in this qubit. So if we had like more carry, so for example, if we had 0, 1, 1, and we wanted to increase it by 1, so this is actually 3 plus 1, which is 4. So the integer values are on the list, so 3 plus 1. So we are starting from the right-hand side, so 1 plus 1 is 0, carry is 1, 1 plus 1 is 0, carry is 1, and yeah. So I'm sure that all of you know how binary numbers work, so you might be wondering like why I'm showing that, but I'm showing that to explain why this order makes sense, that the qubit with the least power of 0 is the first one, because we are always starting to add the numbers from the right-hand side, and then the next qubits will carry the carry. Okay, so let's get back to the notebook. So when we focus, we already saw on the whiteboard how to show how to do this, how to perform this circuit for the input 1, 1, and the sum is equal to 2, but for sure we can't have 2 as the output. We need to have it as 1, 0. So now you have task number 2, and you need to implement the same procedure, this time adding the first 3 bits. The sum will be stored in qubits 3 and 4. So Q3 should be, let me check it. Q3 should be for the sum, and Q4 should be for carry, when you are adding 3 bits, the maximal value in integers is 3. The binary representation of 3 is requires only 2 qubits, so that should be easy to implement. So, and you should, after adding the first 2 bits, it can be the case that Q3 stores 0 and Q4 stores 1, corresponding to the sum. So yeah, you just, in task number 2, you just need to add the first 3 bits. So the input has 3 bits, and store the sum on qubit 3 and carry on qubit 4. You can have 5 minutes for that. Actually, I can see that all of the people who marked that they were working on this task, they said that they finished the task. So if there is anybody who needs more time, please note it on Discord channel workshops, because in the other case we will just continue the work together. Okay, so 5 minutes were a little bit too much, sorry. So we can implement the task number 2 together. So let me paste some comments. So Q3 is the sum and Q4 is carry. I've written here that first always calculate the carry and then the sum, like on the quantum circuit. And I will explain myself in a second. So first of all, we are calculating this. So to the qubit 3, we are trying to add qubit 0. So to do that, first we calculate the carry. So to calculate the carry, we are just using the controlled x, where this is the number that we are trying to add. This is the current sum, and this is the carry bit. So qubit. So if the current sum is 1 and the qubit we are trying to add, then the carry bit should fire. In the first case, it won't fire ever because Q3 is going to be 0 because initially it's 0. So we can skip that, but let's leave it here. And then we are actually adding Q0 to Q3. So Q3 now stores the result QQ3 plus QQ0. So we have the first qubit added. Then we are adding the second, so we can basically copy this code and just change the first qubit, the control qubit. So in here, we will try to find out what the carry is. So if the current sum is 1 and the bit you are trying to add is 1, then the carry should flip. And let's flip it. Yeah, and then we have this controlled x. So this basically says that QQ3 should be QQ3 plus 1. So whatever was the sum before this, then add this first, the qubit number 1. And the third thing we need to do is to actually add the qubit 2 to everything. So once again, we have the carry bit. So the carry should change the sign if the sum is already 1 and we are trying to add 1. And just now we need to increase the sum by adding whatever is in QQ2. So QQ3, after all of these gates, is QQ2 plus QQ1 plus QQ0. And it should be enough, probably. It is. So let me print this circuit. So we could be able to observe how it looks like. So we have too many qubits in here. 5 would be enough. So okay, so what we can see here is that the circuit looks like this. This is the qubit for the sum, and this is the qubit for the carry. When we are adding 1 plus 1 plus 1, that's the maximum thing we can add, like from so 111 is like the maximum input. So the output could be 3, which is 11 in binary. So we just need 2 qubits for that. The first one is for the sum, the second is the second one is for the carry, and we see that that for all the outputs that we've checked, the sum, we can easily check what the sum should be and what's the sum calculated by the circuit, and we see that these sums are equal. Do you have any questions regarding task number 2? There is one thing I forgot to say. So how is this the sum should be equal to and the sum to circuit according to circuit calculated? So the sum should be equal to is very easy. So it's just the integer value, sum of the integer value of the outputs, because of the inputs, because inputs are strings. And according to quantum circuit, so we are measuring the circuit only one time, because like there aren't any like other marked gates, no superposition. We just want to just measure the circuit, and one time is enough because it's going to be like a deterministic result. We are going regardless of how many repetitions of this measurement we take, the result will always be the same. So what we get, there is only, so after the measurement, we get the list of results, but because we repeated the measurement process only one time, so the result consists of only one measurement result. So that's why we need to take the first element of this list. There are no other elements, but we need to take the first one, the only one, and then we get this measurement output has 1, 2, 3, 4, 5 it consists of 5 characters. So it's actually it's not characters, it's integers. So it consists, it's basically a list, and we don't care about what's in the first 3 qubits numbered from 0 to 2, but we care about these 2 ones. And as I've said, we need to multiply it by the proper power of 2. So the first should be to the power of 0, the second to the power of 1, then to the power of 2. So the result is calculated 2 times whatever is on the carry qubit plus 1 time to the power of 0 whatever is on the sum qubit. So that's the way it works. And now we can go to the generalization. So we can review the whole process from beginning. There are a single input qubit A0 and a single output qubit B0, and they are both set initially to 0. So after the operation, B0 equals to B0 plus A0, and B0 can be at most 1. So if they are set, if the initial value of B0 is 0, then it's like no wonder that after we add A0, which could be either 0 or 1, the maximum value is 1. So to calculate whether it's 1 or no, we don't need to use any other qubits. We can just use the qubits we already have and just check if the first qubit is 1, then so at the beginning all of them are 0, but A0 can be 1. So to store the result of A0 plus B0, we just can use the second qubit. So basically we just got rid of the carry bit because there can't be any carry if we are adding 1 plus 0 at most. Otherwise it's 0 plus 0. But if it's 1 plus is 1, this is 0. So this will fire, we will flip this 0 to 1. So the output will be 1, and the output is on the bottom qubit, it's the sum. And if it's 0 and this is 0, this CNOT won't fire, so the sum will be 0. And now we add one more bit, A1. So for now we had A0 and B0 to the summation. At this point, B0 can be 0 or 1. If A1 and B2 are both 1s, then there will be an overflow to the next qubit, since the sum will be 2. So it's not enough to use only these 2 qubits now. And we can check this using CCX gate, where A1 and B0 are the control, and B1 is the target qubit. So you can see that we are basically trying to reinvent the things that we've seen so far in this notebook. So we see that we have the qubits A0, A1, and A2, and we want to store the result of adding this A0, A1, and A2 to each other in the qubits B0 and B1. So first of all, so this is the sum qubit and this is the carry qubit. So first of all, we are adding A0 to B0. And you can notice that there is no this controlled, because we could have a controlled X gate in here. The first qubit should be control, and this will be another control, and there will be X. But when we are adding B0 initially is 0, so we don't need to have this CCX gate because it won't be used. So we start by adding A0 to B0, and this is done with a single CNOT. Then there is possibility of carry, because if this is 1 and A1 is 1, so the sum is 2, it's not enough to use only one qubit, this sum qubit, to represent this result, so we need to have carry. And I said that I will explain why we are applying carry earlier than we are applying sum, because if we change the order, so let's imagine that this carry is after this sum, it is possible that we will change the sign in here, because if A1 is 1, then we will flip, flip the state. We will flip the state B0, and if we do this before we calculate the carry, the calculation won't be correct. So at first we are not changing anything, because this control gate doesn't do anything to the sum, it does only to the carry. And when we don't do anything to the sum, we can just calculate the sum. It's pointless to calculate first sum, and like, okay, you can probably do it, but there will be some other changes in the circuit. So it's easier to calculate first carry, because carry doesn't change these some qubit, but this sum changes some qubit, and the sum qubit is used by carry. So yeah, please do it in this order. So with these two layers, we have added to B0, A0 and A1, and we also want to add A2. So first of all, we are calculating the carry, and second of all, we are just adding this bit. So B0 would be this 2 to the will be multiplied by 2 to the power of 0, and B1 would be multiplied by 2 to the power of 1, and that would be the result. The maximal result in here is 1, 1, which is 3. So now let's take a look at the list of all possible inputs. The inputs, so no, in here we have actually 4 inputs of length 4, which is 2 to the power of 4 possibilities, which is 16 possibilities. In here, in the case here, we could have only 8 possibilities, and it is shown in here how to implement such a circuit for inputs of length 4. And will it be task number 3? Yes, it will. So what I want to show you is that when we have only, so we start how many, so the question is now, how many qubits do we need to store the result? And in the case of adding 3 bits, we needed 2 qubits to store the result, because the maximum result is 3, and 3 can be stored on 2 qubits. Like when we take logarithm with the base of 2 for 3, it's like 2 qubits, and the ceiling of that 2 qubits is enough. And in the case of 4 qubits, the maximum result is 1 plus 1 plus 1 plus 1, which is equal to 4. And to store 4, we actually need 3 qubits, because 2 qubits can store maximally 3, and to store 4, we need 3 qubits. We could store the number up to up to 7 with 3 qubits. So now we will use qubits Q0, Q2, Q3, and Q4 for the input, qubits Q5 for the sum, Q6 for first carry, and Q7 for second carry. And let me take a look at what I can show you now. So yes, can I print the circuit here? I can. So if input is all zeros, okay, a typo, yes. So let's analyze this circuit, and then we will come to the task number 3. So give me a second, please. I will prepare the whiteboard for us. Okay. So we know that the result will consist of 3 bits. So we know that this is like this sum, this is carry 1 and carry 2, but we can store them, like we can name them using like better convention. So let's say there are B0, B1, and B2. That is some weird line. I just want to erase that. Okay, never mind. And we are adding, if I'm not mistaken, we're adding, no, we have too many qubits in here. Sorry, I didn't notice that. You can safely ignore the last qubit because we are not using it. I don't know why we have 7 qubits in here. No, we just, okay, why we have 8 qubits, we just need 7. So you see that that we have some first carry, second carry called B0, B1, B2. So the final result would be read from the bottom to the top. So the number would be B2, B1, B0, which is, so this will be like in the binary representation, and in the integer representation, it will be 4 times B2 plus 2 times B1 plus B0. And now let's see what are the parts of this addition. So we are adding actually 4 bits. So let's say it's A1, A2, A3, and A4. And at first, we are just adding A1. So this is done in here. There won't be any carry because B0. Okay, this is too high. Okay, this is better. So this is B0, B1, and B2. And what we see is that we can only store the result of this addition in this qubit. Then we are adding A2. So when we are adding A2, so the maximal possible result in here, so in the purple part, the maximal possible result in integer is 1. It could be 0, but the maximal is 1, and it's represented as 0, 0, 1. So if the maximal possible result after this second layer is 2, so it's 0, 1, 0, and that's why we need to use the first carry, because we might actually need another qubit. then we are adding another one. So the maximal result could be 3. It can be both. Okay, it can also be 0, 1, or 2, but the maximal result is 3, and we need to be ready for that. But we still don't need to use any more qubits. 2 are enough. So, so the result now should be, the maximal result is 1, 1, but we don't need another carry qubit. And after that, so we've already added 1 plus 1 plus 1, which is, or anything in between, but we just need 2 qubits to store that. But if we want to add 4, like add 1, so it will be like 4th one in a row, the maximal result would be 4. And to store 4 in binary representation, we will need another qubit. So that's why we have another bit 4 carry in here, because 2 qubits are not enough to add 1 plus 1 plus 1 plus 1. Do you have any questions to that? Okay, so now your task will be to implement this exercise number 3 using the given idea, add the values of 7 bits, namely Q0 to Q6, and write the result on the qubits Q7, Q8, and Q9. So if you have 7 bits, you can use the same version of the circuit, but it will be longer, because the maximal value you can store on 3 qubits is 7. So yeah, your task now is to just add this 7 qubits, and you can have 6 minutes for that. I can see that you're still working on the task, so there will be 2 minutes more. The time is up, so let's try to write this task together. Right. Yeah, so let me paste my own comments in here. So in qubits Q0 to Q6, we are storing the values that we want to add, and we need 3 additional qubits. 7 stores the sum, 8 stores the first carry, and 9 stores the second carry, and the total result is 4 times carry 2, which is QQ9, plus 2 times carry 1, which is QQ8, and plus the sum, which is QQ7. So first of all, let's add qubit 0. So when we are adding qubit 0, the maximal value we can have is 0 plus 1. So it's just enough to use the CX, and the control is the value we are trying to add, and this is the sum qubits. So if it's 0, then it's the state of Q7 is not inverted, and if it's 1, then it is. So that is just in place addition. Then we are adding qubit 1. So when we add qubit 1, there actually can be carry, because after this addition, this could be 1. It does not need to, but it can be 1. So when we add another 1, the result is 2. So we need 2 qubits to store that. So that's why we need to have the first carry bit. So if the previous sum is 1, and the value you are trying to add is 1, then this carry bit will like be inverted. So if it was 0, because initially it was, then it should be 1. And after you calculate the carry, you just need to add QQ1 to QQ7. So after these 2 steps, QQ7 is equal to QQ1 plus QQ0. Then we are adding qubit 2. So the maximum value is 1 plus 1 plus 1, which is 3. 2 qubits are still enough to add to add 3 bits. So we are doing the same thing we've done for qubit 1. So we're checking if there is a carry. So if the previous sum was 1 and the thing you are trying to add is 1, then invert the value of the carry bit, and then just append to the sum qubit the new value you are trying to add. The next thing we are trying to add is the qubit number 3. So it could be 1 plus 1 plus 1 plus 1, which is 4. To store 4 as the result, we actually need 3 qubits. So it's the time when we will start to use carry 2. So first of all, we calculate like the oldest carry. So if the number you are trying to add is 1, and the current sum is 1, and the current carry is 1, then invert the state of this initial carry 2. So if both of them are 1, so we have so the current sum is okay, already 3, and you are trying to add 1 to that. This represents that there is already 3, and we are trying to add 1 to that. Then this should flip. So we calculate the carry for the oldest bit. Then we are calculating the carry for the intermediate bit. So if the previous sum is 1 and you are trying to add 1, then invert the value of the first carry. And when we've done that, all of that, then we can just calculate the sum Q7 plus Q3, because all the carries were calculated earlier. And basically we could copy this code 3 more times for qubits 4, 5, and 6, and just change the qubit 3 to the appropriate qubit. So it's more convenient to like implement it using for loops, but let me just paste this longer code in here. So we can see that this code can be just divided into the parts when we are adding, depending on how long the possible results can be in binary, we are adding the gates. So when we want to add the qubit 4, the maximal result is 1 plus 1 plus 1 plus 1, so it's 5. And we need to do the same thing we did for qubit 3. But that's the code, and I'm not going to talk. Okay, there is some string out of range. I will check what's wrong. Okay, yeah, that's wrong. I haven't imported that. So if you got the correct result in here, so the sum should be equal to, and the quantum circuit says the same thing, then you've got the correct result. But I would like to elaborate a little bit more on how this the design of this circuit. So the result qubits are B0, B1, and B2, and there should be read from the bottom to top. So it's 4 times B2 plus 2 times B1 plus B0. And we can see that if in the binary form, it's enough to have only like 1 qubit, we don't need additional carry. So it would be enough to have only like 1 qubit. So in binary, it's 1, then it's okay. Then so we've added 1, like maximum, the maximum value we've added in here is 1. In this step, like when assuming that in the previous step we already added 1, the maximum value in here is 2. If we didn't add 1, it's not a problem. It will still work. It's just as long as you have 0 here, this CNOTs won't fire. So we don't need to care about a value smaller than 2. So to store 2, you need 2 qubits. To store 3, you need 2 qubits, and to store the values from 0 to 7, you just need to have 3 qubits. And that's why we are applying this controlled x, because you just need to check if the next carry should be applied or no. And do you have any questions to task number 3? Okay, so it's 5:45. I think a 5-minute break will be nice. So let's meet at 5:40. The break is finished, so let's get back to our notebook. So now we are going to check whether the number is equal to something. So let's assume we have two qubits, Q0 and Q1. I've already printed the circuit for that. So this is Q0, this is Q1, and they store an integer. And we want to check whether this integer is equal to 3. We have a qubit Q2, which is the output qubit. And at the beginning, it's initialized to 0. So maybe let's have everything initialized to 0. So that's just the circuit. And we apply X gate on Q2 if both Q0 and Q1 are in state 1. And this circuit implements that. And it makes sense because 3 in binary is 1, 1. So both 0 and 1 should have this value. And there is the note that B1, B0 is the value. So when we read the value, is this qubit is the oldest one, and this is the youngest one. So actually, when we want to add, when we want to check whether the input is 1, 1, we can set the input to 1, 1 by using the X gate on qubits 0 and 1, which are the input. So if 0 is 1, and so if Q0 and Q1 are 1, this is done by that, then this Toffoli gate should fire, and the measurement result should be that actually, yes, this number is equal to 3. When we have some other case in which the number is 2, so it's 1, 0, this Toffoli gate won't fire because it's not equal to 3. So it's actually a very nice way using this controlled knot to check whether the number is equal to something. So such a check is trivial when the binary representation of an integer contains only ones, because a multi-controlled NOT gate is applied to the output bit. And suppose that we have 3 qubits, and we are interested in checking whether their value is 101, which is actually 5 in the decimal number. In this case, the value of the output qubit is flipped if the first qubit is in state 1, okay, the second qubit is in state 0, and the third qubit is in state 1. We use a multi-controlled NOT gate. All the control qubits should be in state 1. Therefore, this time we do a pre and post processing for the middle circuit. We apply X gate so that the second qubit can be in state 1, but this will be in state 1 just for a second. So this will be in state 1 when we want to apply the multi-controlled NOT gate, which is originally 1. And after we apply this gate, we can just apply this X gate once more to return this second qubit state to its original state. So now your task is to implement the exercise number 4. And you need to check whether the first 3 qubits, so qubits QQ0 to QQ2, store the binary representation of number 5. And the output should be returned on qubit number 3. Do you have any questions regarding what you need to do? Okay, so I think 4 minutes, you have 4 minutes from now to finish task number 4. let's do this task together now. So we need to store the output on qubit 3, and we will be using this multi-controlled NOT gate. So let's write that. So we are using multi-controlled X gate. The target is qubit with ID 3, and it's controlled by qubits from 0 to 2. But we are looking for the state for the number 5, which can be represented in binary as 101. So this like normal version of the multi-controlled NOT gate won't work. We need to artificially change this second qubit state, which is actually the qubit number 1, to 0, and we will do that just for a second. And then by a second, I mean just for the time when we need to apply this multi-controlled NOT gate. And we then after the gate, we can like just reverse what we've already what we've done. So the number we are checking in this for this input is actually 5. And what we are doing is so how does this work? So we have the input initialization here. So it's 101. Okay, the 101. This is 0, so we need this to be 1 because we want this multi-controlled gate to work. And if you like take a closer look at this wire, we can like just ignore this at, and we have identity gate, and in here it's x multiplied poly x multiplied by poly x, which is the identity gate. So nothing changes on qubit 1. So this was just a trick to make this multi-controlled NOT gate fire. And we can also change the input. So now the input would be 0, 1, 1, which is 3, and it is not equal to 5. Yeah, 3 is not equal to 5, and that's correct. So that was an equality constraint. Now let's move on to inequality constraints. So if there are two qubits, Q0 and Q1 storing an integer, and this integer is equal to Q0, sorry, and this is equal to Q0 plus 2 times Q1. So Q1 is the oldest bit, and we are interested in checking whether this integer is greater than or equal to 2. In this case, we are interested in checking whether the value of the two qubits is 1, 0 in binary, which is 2, or 1, 1, which is 3. In both cases, the qubit Q1 is in state 1, and we are not interested in the state of qubit Q0. Hence, the output should be flipped if the qubit is in state 1, regardless of what happens on the qubit Q0. We can check this using a CNOT gate where Q1 is the controlled and Q1 is the target qubit. So let's see that. So yeah, it should work. We don't need that many qubits. 3 are enough. Yeah, so the binary number represented in here is 2 times this, the value from this qubit plus this qubit. So if it's just this top qubit, it won't ever be enough to be 2. But if it's the value from this qubit, it's if this qubit, the state of this qubit is 1, then the value is always at least 2, because it's 2 to the power of 1, which is 2 times 1, which is 2 again. So we just need to check whether this qubit is set to 1, and it actually turns out it is. So for this no, it's actually not set to, okay, I've just printed the circuit in here, but it is for the inputs 1, 0. No, for the inputs 0, 1, because that's the most important, not most important, but the first bit from the left hand side. and from the state 1, 1. For the state 0, 1 and 0, 0, it's not, because we will have, okay, maybe I can print all the circuits. It's only 4. So here we have state 0, 0. So the identity gates here, this CNOT gate won't fire. In the case of the input 0, 1, so it's 0, 1. The binary value is 1, 0, which is 2, and the CNOT will fire. So yes, the answer would be, answer is stored on qubit 2. So the answer would be that yes, it's greater than or equal to 2. If the input is 1, 0, in binary it's 0, 1, which is 1, and 1 is not greater than 2 because this this CNOT doesn't fire, so the result is 0. And if the input is 1, 1, so we have axis here, then this is the output, which is stored in here, is it says that this input is greater than or equal to 2. We can do another thing, which is instance many number checking. So we explained how to check the equality and inequality constraints. While classical computers are restricted to check one number at a time, quantum computers can do it instantly on a superposition of states. Hence, we can create a superposition of all possible integers represented by the input qubits using Adamart gates. And then, using the method above, we can check for equality or inequality constraints for the integer superposition. So basically, what this says that if you remember that we are going to implement the Grover's algorithm, the initialization step of the Grover's is applying equal superposition to all the states. So this paragraph says that we can also do this number checking on a superposition of states. So the circuit below has 4 qubits 0 to 3. The first 3 qubits hold an integer, and the last qubit is the output that returns the decision whether the input is greater than or equal to 4 or not. Note that when you measure, you will observe only one of the numbers and whether it is at least 4, because we just need to measure this many times to have like different outputs, because it's not a deterministic result here. So what we can observe is that when we want to check whether the input is greater than or equal to 4, we just need to have a single CNOT gate in here, because this is 2 to the power of 2 multiplied by whatever is on this wire. So it's 4 multiplied by whatever is here. So it will be for sure at least 4. From the first 2 qubits, we can get the maximum value could be like 3. So it's not enough to be greater than or equal to 4. So when we run it multiple times, depending on what we have here, so it could be either 0 or 1, we will get whether the result is greater than 4 or no, or equal maybe to 4. So in general, yes, you're allowed to use the Adamart gates with this type of comparisons, and you just need to take care only of some qubits. For example, if you wanted it to be greater than or equal to 5, you would also need to have that's the task number 5. Okay, so now we are coming to task number 5. Design a circuit that checks whether the first 3 qubits store either 4 or 5 in binary, and you have 2 hints. The first one is that 4 in binary is 100 and 5 is 101. Hence, the qubit I did with 2 has to be set to 1 and Q1 to 0, and Q0 can be arbitrary. So these 2 qubits should be the way they are. So it's either it is 1 and 0, and the last one can be 0 or 1. And so you would need to do this very interesting thing with applying X gates, because you're also checking for 5. And the last thing is that please be careful with the order of the qubit values. So this is qubit Let me check. This should be qubit 1, qubit 2, and qubit 3. Oh, sorry, we are starting from 0, so it's 0, 1, 2, and it's already written in here. So this is qubit 2, 1, and 0. Okay, you have 4 minutes for task number 5. Time's up, so let's implement this task together. So first of all, let's see what we already have implemented. So we know that we have the Hadamard gates on the first 3 qubits, and then we have the qubit for just the result. And what we know is that we are looking for 101 or 1 100 or 101. So we know that this qubit Q2 has to be 1 and qubit Q1 has to be 0. So we can implement it the following way. So for the multi-controlled node to work, we need to have the qubit Q2 set to 1 and Q1 set to 1. So we know that Q1 should be 0, so we need to have this this as like not the value it is, because it should be, if it's 1, if it's 1, then it's a wrong number, and if it's 0, it's the correct one. And we also like reverse this operation. We need to also reverse this operation because we don't want to change the input. We are just doing this trick to have this multi-controlled node working. And when we run this multiple times, we can see, so basically we don't know what was, because at first we have an equal superposition of all these, of all the results. So we can like run it multiple times and hope, okay, number measured is 6. So it's 1, 1, 0, but this 1 is flipped in here and 0, so it's not 4 or 5, neither nor 5. That's maybe okay. How many times do we need to try to have? Oh yes, finally it turned out that we actually had 1, 0, 0, and it got measured. We needed to try it many times because of this Hadamard gates. There is equal superposition, but when we measure, we just are getting like some version of all the 8 possibilities. So yeah, we need to try sometimes many times to get what we want to have. Yeah, 7, 3, 3, 7. Okay, we are now like, yes, okay, another 4. So yeah, you see that when we measure, we are just collapsing this state. And this brings us to the last notebook of today, where we will use all the knowledge both from the max-cut problem and from the others and numbers. So Groover's algorithm for the max-cut problem. Finally, we're ready to implement the whole algorithm. So for the initialization, we will apply a layer of Hadamard gates that will represent the color of each vertex. So at the beginning, we are assuming that so this is basically just trying to apply all of the possibilities. So at first they have equal probabilities, but then we will just modify probabilities. We know how to implement the Grover's diffusion operator. We saw that yesterday in notebook B01. There was diffusion somewhere towards the end, yes. So where is the gate representation? That's the operator for diffusion. And now we need to implement an oracle, which will mark the colorings in which there are k edges whose endpoints are colored using different colors. So what we see is that we are looking for k edges, so we need to like calculate how many edges have this specified coloring. And we need to implement the oracle, so this not transparent box that marks the correct solutions. So first of all, we need to implement edge checking for each edge. And edge checking, if I'm not mistaken, was implemented in here. So if, for example, in task 4 in a notebook B02, we were checking whether the edges that are connecting vertices in some graph are connecting vertices with different colors or with the same. If with different colors, the value was 1. If with the same, the value was 0. So that's how we can check the edges. Oh, sorry. Then we need to sum the outputs of the edge checking step. So that's the knowledge we have from the notebook B03. If we want to add multiple numbers, for example, in task number 3. Yes, in task number 3, we learned how to add many numbers to itself. So actually it was 7 bits. So we will see how many we need in the Grover's algorithm. Then we need to check whether the sum is equal to or greater than k and save the flag on the auxiliary qubit. So that's the thing we've just done in task number 5 here. So we were checking whether something is equal to something else or not. And then we just need to implement the Z gate on the auxiliary qubit. Yeah, because in the Oracle, we just want to mark this correct coloring. And to mark the correct coloring, we are using the Z gate, because if the coloring is correct, the state should be 1. And after the Z gate, this 1 will be, the amplitude of the state will be flipped to like from 1 to -1 and from -1 to 1. And this is the Oracle. The Oracle works for the decision version of the problem, which checks whether there exists a coloring such there are at least k edges. So we are not solving this task per se. We are not just trying all the different colorings and then we are trying to return the best coloring. No, we are just are considering the decision version of the problem. We say how many edges we expect to cut, and then we are checking whether this coloring exists, but we don't know if this cut, like this edges, is the best outcome. And suppose that k is a 3-digit number, b2, b1, b0. First, we should check whether there is a coloring such that b2 is equal to 1. If it is, then we check if there is such a coloring that b2 is equal to 1, then b1 is equal to 1. So we are basically trying to check all of the possible colorings. So we are trying to, we are doing a binary search of all the possible colorings. So yeah, maybe let's just do an example together. So let us consider the following graph. We have 0, 1, 2. So you probably can see that the best idea would be to have 0 and 2 have the same color and 1 have different, then the cut would be 2. So we can check whether there is a cut with like equal to 2. So what do we need to do? We will check whether there is a coloring such that 2 edges connect vertices with a different color. So as I said, 2. This number of edges is 2. To check that, we will verify whether then for number b1, b0, b1 is set to 1. So yeah, to store the result of the addition, you need to have 2 qubits, because the sum of 1 plus 1 is 2. And to make sure that this number is equal to 2, you need to just use 2 qubits. So how many qubits do we need to use in total? So we need to represent these vertices using 3 qubits. So qubits 0 to 2 are designated to vertices. Then we need another 2 qubits to represent the edges. The first edge is 0, 1, and the second is 1, 0. Then we are going to need 2 qubits for storing the sum. The maximal sum is 1 plus 1, which is 2. So 2 can be stored on 2 qubits. And we need to have a single qubit for storing the result, actually. Since qubit 7 stores is a flag, so it stores a flag. It's whether b1 is set to 1 or no. we will apply the Z gate on that qubit. So to check if the sum is equal to 2, we just need to check one of the qubits. So qubit B1, do I have a picture for that? So maybe not necessarily, but it's not a circuit for this problem, but this B0 and B1 refer exactly to the same thing. So if we want to check whether the number is at least 2, we need to make sure that B1 is the value of B1 is 1, because it's B1 times 2 to the power of 1, which is 2. And on this auxiliary qubit, we store whether this cut has this property, or this coloring has this property or no. And if it has, we should flip the amplitude with for that coloring. And how does it work? So the Oracle computations consist of all of that. So first of all, we need to implement the edge checking for each edge. So that's the task we implement task for notebook B02. So basically, we are applying check the edge 01 and store the result in qubit 3. So it's applying C0 when the control is 0. Target control is qubit representing qubit 0, and target is the qubit representing the edge 01. And then vertex 0, edge 01. We are doing the same for the edge 1, 2. So we are storing this result in another qubit 4. So storing qubit 4 whether the edge between 1 and 2 is the edge between different colors or no. Then we need to we are using qubits 5 to 6 to store the sum. So the sum could be maximally could be 1 plus 1. So qubit 5 is used for the sum, and qubit 6 is used for carry. So after this step, the sum could be at most 1. And after this step, the sum could be at most 2. And what we need to do last is to check whether the sum is equal to or greater than 2, and save the flag on the auxiliary qubit, which is qubit 7. So if the sum, that is from here, and the sum could be, the sum is, so this is on qubit 6, we are storing B1. Yes, the most important one in here. And on qubit 5, we are storing B0. So what we need to check is whether this B1, which is qubit with ID 6, is equal to 1. And if it is, then we know that, first of all, we had these edges, and yeah, their sum is equal to 2. And in the oracle, what do we need to do is we are just applying the oracle. Then we are changing the amplitude of the marked state. And in fact, if the state is marked, then we will flip its amplitude, and if it's not, we won't. And we are inversing the oracle computation, because we want this auxiliary qubits, so qubits 3 to 7, to be restored to their original values of 0. We have already implemented the Groover's diffusion operator. So it's the same as we've seen in this notebook, and this diffusion allows us to increase the amplitude of the marked state, and if we increase the amplitude, then we increase its probability. Then we are running the 2 steps of the oracle. So somebody calculated that there are 2 steps needed. And let's run that. So random guess probability is 12.5%, and it makes sense because there are 3 states. So it's 8 possibilities, 1 divided by, no, it's probability. So it's something else. Yeah, but its amplitude squared is 12.5%. But in here, we get the probability of observing 101 50% and 010 50%. So it means that that the results we get. So how to interpret these results? So 101 means that this and this should be in the same color, and this should be different. So it should be blue, red, blue, or the other way around. This should be red, blue, and red. So we can see that the that we were able to get a cut with equal to 2 edges. And now your task would be to implement either exercise number 1 or exercise number 2. Both of these exercises have the same purpose. The only difference is the graph you need to implement. In here you have 1, 2, 3, 4 edges. In here there are a little bit more, 1, 2, 3, 4, 5, 6, 7 edges. So it's up to you to choose which task you want to implement. You will have 15 minutes for that, and when the time is up, I will show the implementation only for task number 1. So you have 15 minutes from now. I can see that people are still working, so another 5 minutes. I can see that some of you have finished, but some other people asked for more time. So I think we can, so for the people who are still working, you can work on this task, but for the people who are not, let's meet 5 minutes from now, which is actually this time. The break is finished, so let's come back to the Grover's algorithm for maxcut problem tasks. I will solve the task number 1. So before we start, we in task number 1, we need to check whether there is a coloring in which there are exactly 4 edges. connecting vertices with a different color. And we can see that 0 and 1 should be in one set and 2 and 3 in the other. Then the cut is exactly 1, 2, 3, 4. So let's discuss this. So this is the size of the cut. We know that the qubits 0 to 3 are dedicated for vertices. We have 4 vertices. We have 4 edges, so we need to have another 4 qubits for edge checking. Then we would need to calculate the sum, and the sum is up to, like, we're looking for 4. So 4 in binary is 1, 0, 0, so we will need 3 qubits to store the sum. And we always need an auxiliary qubit that will check whether the sum is equal to 4. So we are going to follow these instructions. So first of all, we are going to implement edge checking for each edge, then sum the outputs of the edge checking step. So this is the first step. Second step, the third step is check whether the sum is equal to or greater than 4. And then we would need to apply the Z gate on the auxiliary qubit, because in the oracle we want to mark the correct colorings. So let's start with designing the oracle. So there is one inconvenience in here. So let's start with designing the oracle. So first of all, we need to follow the steps. So we are going to implement edge checking for each edge. So I will paste the code and explain it line by line. So first of all, we check the edge 0, 2 and store the result in qubit ID'd with 4. So this is done with the CNOT gates. Then we are doing the same for the edge 0, 3, and the result is stored in qubit 5. Then we are doing the same for edge 1, 2, and the qubit to store this result is qubit 6. And then the last edge to check is edge 1, 3, and the qubit to store the result is qubit 7. So on qubit 7, store the result for edge 1, 3, on qubit 6, edge 1, 2, on qubit 5, edge 0, 3, and on edge 4, on qubit 4, edge 0, 2. So that was the first step. The second step is to actually sum the outputs of the edge checking step. So for the outputs, we will use the qubits from 8 to 10 actually. So the qubit 8 is for the sum, qubit 9 is for the first carry, and qubit 10 is for the second carry. So let me write this code here. Okay, I pasted it actually. So first of all, we are adding so QQ8 is for sum. Maybe I can write it somewhere. Okay. Yeah. So let me write this comment. QQ8 is sum. QQ9 is 9 is the first carry, and QQ10 is the second carry. Carry 2. So the number, in fact, is 4 times carry 2 plus 2 times carry 1 plus sum. So the first step is to add the edge result, which is stored in qubit with ID 4. So this can be stored only in sum, because the maximal value is 1. In binary, it's also 1. Then we need to add the edge results stored in qubit 5. So first of all, we are calculating the carry, because the maximal value could be greater than only storing it in 1 qubit. So this is the carry. So if the current sum is 1 and the value you're trying to add is 1, then there will be this carry and then just sum. So to the qubit with ID 8, just add the value for the edge 03. Then we are doing the same for the next edge, which is edge 1, 2, stored in qubit 6. And after that, the maximal value we can have is 3, which in binary is 1, 1. So we need only 2 qubits to store that result. But actually, after this step, we have one more edge, and this can up our sum up to 4. So to represent 4, we actually need 3 qubits. So we will have this carry 2 also. So this carry 2 is a multi-controlled X gate. And this X gate is applied to 10th qubit because that's the last qubit we need for the sum. And it's controlled by all the other qubits that are used for the sum. So qubits 7, 8, and 9. So this is the first carry, the most important carry with the weight 4. So it's carry 2. Carry 1 is just a CC0 gate. And the sum is calculated in here. So to calculate if something is 4, we need 3 qubits. And the last step is to check whether the sum is equal to 4. Maybe let's just focus on equal to 4. So the binary representation for 4 is 1, 0, 0. And we need to read it from right to left. So Q00 should be, so Q8 should be 0, Q9 should be 0, and Q10 should be 1. So it's 1, 0, 0. And to check that, we need to use this trick with inversing, flipping the state of the qubit before we use the controlled gate, because we want to check if all of them are if all of them are 1, but we know that before they are 1, they should be 0. So to have this 0 turn out to be 1, we need to first apply the X gates and then reverse these X gates. So that was the step number 3. And the step number 4 was to apply the Z gate on the auxiliary qubit, but we will do it in the Oracle computation. So we know that in the Oracle computation, we just want to reverse the Oracle because there are going to be, they said it somewhere, there are going to be 2 iterations of this reverse search. So we are applying Oracle. Then we are applying the Z gate on the auxiliary qubit because this actually tells us whether this state should be marked or not, because in this is the step on qubit 11. We actually store the result, whether this coloring allows for the number of edges cut equal to 4. So we need to mark whether this state does that, and we are just inversing this Oracle to still have the state with a different amplitude with a different sign than the other amplitudes, but after that we just want to change the sign of the qubit, change the value of the qubits from 4 to 11 to 0. So we want to restore these qubits. And what we also need to do is to implement Gruber diffusion. So that's the thing that was implemented in here. And the Gruber, so we and if you were wondering on which qubits do you need to apply this Gruber diffusion, so after this Oracle, so Oracle is the first step and diffusion is the second. So after Oracle, only the first 4 qubits representing the vertices have some meaningful values, because the other ones. So from 4 to 11, actually we've like restored them to 0. So this oracle should only work on these first 4 qubits representing the vertices, and the diffusion. Okay, something, I don't know why. Yeah, I know why. Maybe I can't. So what happened here? In the Grover diffusion part, we are going to apply a layer of Adamart gates, then the layer of X gates, and it's all for the qubits from 0 to 3. Then we are applying the Z gate on the last of them, and we are like reversing the layer of X gates with the layer of X gates, and the layer of Adamarts with the layer of Adamarts. So it's all performed for the first qubits, actually first 4 qubits representing the vertices. And yeah, basically that's all. If you are using this code, please make sure which oracle you're putting in this computation. So I'm using Oracle computation instead of Oracle. And let's see the results. So if we were choosing randomly, so the probability of making a random guess that will be correct is a little bit more than 6%. But with our algorithm, we are expecting the cut 1100 or cut 0011, which is basically the same cut. It means that the first vertex 0 and 1 should be blue and 10 red. So no 10, sorry, 01 blue, 23 red. 01 blue, 23 red makes sense, or 01 blue, no, red, and 23 this other color. Yeah, this should be the opposite colors, so this is basically the same solution. And so this has like a little bit more than 47% probability. This has this is more or less the same. So these 2 solutions are we get them with very high probability. So it's much more than 90%. And these other solutions, they can occur because the amplitudes for incorrect solutions are not 0, but the probability of having them is pretty low, like 0.4%. So yeah, that's all from my side. So today we've finished all of the notebooks that compose the QNickel workshop. So I would like to thank you very much. If you have any questions, it's perfect time to ask them, or you can ask them later on Discord, however you prefer. And good luck with solving the quizzes. That's all from my side.
Hey, great, thank you. Thanks, Justina. It was a great lecture as always, so thanks for that. I don't see questions now on our Zoom, so I think we should we can finish soon. So maybe just to remind all the participants, you have 1 week to complete all the homeworks, all the quizzes, and then hopefully in November we'll be able to send the certificates to those who just obtain sufficient amount of points. And if there are some questions, you can ask your questions still on the Discord. We'll try to answer. Some of our mentors might be less active than they were during the workshop, but we'll try to reply, of course. And I think that this is all from my side as well. So there's a question from Mateusz. Yes, so Mateusz, if you want, you can unmute yourself and ask.
Okay, so do you hear me?
Yes, I can hear you.
Okay, so I unfortunately missed the Cirque introduction, so I rewatched a part of the previous lecture, but I wanted to ask if there is a certain advantage over like Qiskit and Cirque. Is there one preferred in over another in some situations, or is it total preference? I don't know if the question makes sense
Yes,
or yeah.
I think it makes sense. Justina, can you try to answer?
Yeah, this question makes sense. So I think that as of now, I can't think if there is like a preference to use one of this framework over the other. So I think it's up to somebody's preferences what they would like to use, because sometime in the past there was TensorFlow Quantum, which is based on Cirque, and Qiskit was not integrated with anything for quantum machine learning, but it's not the case since at least a year or maybe more. So as of now, I think that both of the frameworks have similar powers.
I imagine there is a bit of a difference if you're using real quantum computers, that is Google or specific hardware. Google prefers Cirque because they're the ones that make it, and IBM prefers Qiskit. So probably if you want to write something for IBM computers, you might have better experience with Qiskit. Everything will just work there. You might have to play a bit more with.
That was actually my another question: is the difference between the hardware operating, or is it like one is based on another?
I mean, both are
example.
currently fairly general from my understanding. That is, the standards kind of converged, things opened up a bit. So it isn't such a big difference as it was in the past. Basically, last I checked, almost every provider will offer will work with Qiskit, and I think Cirque should be similar by now.
Oh, okay, nice.
All right, do we have more questions now? There is also a link found by Dominic, and he shared it on the chat. Good. I don't see more questions now. So Justina, I think we can close this session. Good, thank you. So I will now stop recording.